name is Chris Harris and I'm from AlleryTutors.com, and welcome to this video on exam papers. So in this video we're going to look at the AQA Chemistry Unit 1 May 2014 paper, and the whole point of these is we're going to go through the questions of these papers and give you some little tips and techniques to make sure that you can get all the marks possible in the A-level chemistry papers. So it's really important because when you're studying chemistry, you need to make sure that not only do you know the content, but you actually know how to answer the questions as well. And we call that exam technique, and that's what I aim to go through in these videos. Okay, these things are also available on the AQA website. So you might want to download this paper, have a go at the question yourself, and then you can run through this video to see if you've got it correct and to make sure that you've used the right technique as well. If you don't want to look at the first question, you can pick any question you want in this video. They are sectioned off as well. Okay, so let's make a start and we'll look at question 1 first. And you can see here question 1 shows us a table about fundamental particles in an atom. It shows us some very specific masses here, and you can see they're all to 4 decimal places, so they're very precise numbers. And what it's asking us to do is an atom of hydrogen can be represented as H1. Use the data from table 1 to calculate the mass of this hydrogen atom. So we need to know what's in a hydrogen atom first. So a hydrogen atom will consist of a proton and an electron. It doesn't contain any neutrons at all, and it contains one of each. So all we do is we write down 1.6725 times by 10 to the minus 24, and we're going to add that to 0.0009 times by 10 to the minus 24. And if we put that in our calculator, we should get 1.6734 times by 10 to the minus 24, and that should also be in grams. Now there's your final answer. So that would get you the first mark. Okay, so if we look at the next question, and this one is, which one of the following is a fundamental particle that would not be deflected by an electric field? And we've got electron, neutron, and proton, and we just have to write the correct letter in the box. So an electric field, any subatomic particle that is affected by an electric field will have to have a charge itself. So an electron has a negative charge, a proton has a positive charge. Because the neutron has no charge, it won't be deflected by an electric field. So the answer here is going to be B. So there's your second mark. Okay, so if we look at the next question, bring that down. Okay, so we've got question 1b, and it says a naturally occurring sample of the element boron has a relative atomic mass of 10.8. In this sample, boron exists as 2 isotopes, boron 10 and boron 11. Calculate the percentage abundance of boron 10 in this naturally occurring sample of boron. Now, this question is actually pretty difficult. It's not an easy question to do, and you do need to know a little bit of algebra to do this. But this is actually talking about relative atomic mass. So we have to use the equation to work out the relative atomic mass. And so we're just going to write this here. And that's going to be mR, which is the relative molecular mass of this. Or you can use atomic mass because that's what we're using. So let's change that to AR. And the equation we need to know is the isotopic atomic mass. So the AR of the first one, which is number 1, which I'll come on to in a minute, multiplied that by the abundance, and we're going to add that to the isotopic mass, or the atomic mass, of element 2, or isotope 2, times by its abundance. Okay, and all of this is going to be divided by 100. It just makes it a lot easier if we turn these into percentages. Okay, so the key thing is we actually know the relative atomic mass of this anyway, and the relative atomic mass is 10.8. So that's what we're just going to put here. So the relative atomic mass is 10.8. Now, normally in the equations, you have to work out the relative atomic mass, and you're given the abundance of the two isotopes already. So this one, they're doing it back to front. So they've given us the relative atomic mass. Now, what we have to do is this is where the algebra comes in. And we're looking at the isotopic atomic mass of the first element. And we're going to say this is boron 10. So what I'm going to do is I'm going to replace the isotopic mass there with 10. And we're going to call the abundance X because we don't know the abundance. It hasn't told us that. So we're just going to put X on there. Okay. And we're going to add that to the isotopic mass of the next one, which is 11. So we're just going to put 11 there. Now, the key thing with this is that we don't know the abundance of this second isotope, but we do know it's got to be 100 minus whatever the abundance of this is. So that's what we're going to put here. 100 minus X. We're going to close that bracket, and you can see we've got a little bit of algebra going on here, and we're going to divide all of that by 100. Okay, so what we're going to do is we're going to try and get rid of all this rubbish here, and we can do that by expanding the brackets. This is where the algebra comes in. So we take the 11 and we're going to multiply that by 100, and our first answer should be 1100. And we're going to do the same with 11 times by minus x. So we're going to put minus 11x, which goes there. So effectively what I've done is I've simplified this and we've rewritten it over there in a different form. Okay, so what we're going to do then is we're then going to try and simplify it. We need to work out the value of x in this case. So to do that, we need to get rid of this 100. So we need to multiply this side by 100. And we need to multiply that side by 100. So if we do that, we should be left with 1080. Okay, and then that should equal, and this should just be 10x, which we're just going to put there. And we're going to add that to this bit here, which we worked out over there. And that's going to be 1100 minus 11x. Okay, so then what we have to do is we then have to try and simplify this and then rearrange it. Now you can see here that we've got 10x minus 11x. We can simplify that, and that can give us minus x. So if I rewrite this out just over here, just in a more simplified form, so we've got 1080 equals, and if we put 1100 minus x. So all we've done here is we take the 10x and minus 11x from there. Okay. And then once we've done that, you then need to try and get x on its own. But we've got a minus x here, and that's not very nice. So we need to try and shift this across to the other side of the equation to turn it into a positive x. And we need to shift this number across over there. So I'm just going to represent this with arrows. So we're going to shift this minus x over to this side, which will turn it into a positive x. And we're going to get this over onto this side to bring it over so we can get x on its own. And what that should leave us with, if we rearrange this, we're running out of a little bit of space here. This is x will equal 1100 minus the 1080. There we go. And that should give us 20%. And that is the abundance for x. So this number here should be 20, and obviously this one should be 80. Okay, so you can see that was quite tricky, that one. And if we look at the next one, which is 1b, part 2, see a state in terms of fundamental particles why the isotopes B10 and B11 have similar chemical reactions. And the key thing they're looking for here is they're looking for the same number of electrons, because that's the key thing that you need to know. So write that down. There you go. Or the electron configuration is the same. It's only for 1 mark, so they're not after a lot, so you don't need to write too much. So we'll just put that on there. Electron configuration. All right. Okay. So it's only 1 mark, like I say. Okay. The next one. These ones are quite popular with the examiners. So this one is a set of data, ionization data, and they want us to complete this table by suggesting a value for the third ionization energy of boron. So you can see here we've got different numbers going across here. Now, if you look at a periodic table, you should find out that boron is in group 3. Therefore, the amount of energy required to remove the electron from that third group isn't very high. So therefore, we need to put in an ionization energy that shouldn't be too far away from here, but again, significantly smaller than this number here, because the fourth electron in boron is in a shell a lot closer to the nucleus. And so that's why this energy is very, very high. But the third electron in boron is still in the same shell as these. So the number shouldn't be too different. So we're looking for, you could put a number in something like 4,000 in there. However, the mark scheme will actually accept a number that is between 3,500 and 10,000. But it can't be anything bigger because it can't be too close to this because the electron is in the same shell as these two. Okay, so the next one, which is 1D, and it says write an equation to show the process that occurs when the second ionization energy of boron is measured. Include state symbols in your equation. Okay, so all we have to do, and this is the key thing, is the second one. We know the element is boron, so second ionization means we've already removed an electron from the atom already, so we're going to start with B+, and we're going to remove the second electron from this, and that will give us B2+, plus an electron. And the key thing is that you include your state symbols as well. It is only one mark, but state symbols are crucial. All according to the definition for ionization energy, you always have to have your ions in the gaseous state. That's really important. Dead easy to remember, so you don't need to worry about state symbols of anything else. Okay, and the final question, number 1, it says explain why the second ionization energy of boron is higher than the first ionization energy of boron. And the main reason is we are trying to remove an electron. So write this down on here. There you go. We're trying to remove an electron from a positive ion. Now that's going to take a lot of energy. If I can spell it right. That's going to take a lot of energy to do because it's something that's already positively charged. That electron is going to be attracted quite well. So we're going to need a lot more energy is required. Okay. And so that's it. And you can see we should have 8 marks in total if you manage to get them correct. I would say the most difficult question was certainly the algebra one that we just did before there. But let's look at the next question. Okay, so this is question 2, and this one is on amount of substance. So you can see if we look at the example they've given us, it says when heated, iron 3 nitrate with an MR of 241.8 is converted into iron 3 oxide, nitrogen dioxide, and oxygen. So here's our iron nitrate. It's a solid, and we're going to form iron oxide and nitrogen dioxide and oxygen. And they've also told us the state symbols. So we've got solid, solid, gas, and gas. Okay, so it says a 2.1 grams sample of iron 3 nitrate was completely converted into the product shown. So that tells us the whole lot was converted into the product. Calculate the amount of moles of iron 3 nitrate in the 2.16 gram sample. Give your answer to 3 significant figures. So this is a classic mole calculation. So we're just going to write down our equation. So number of moles equals the mass divided by the MR, which is the molecular mass. Now they're very kindly given us the MR of the nitrate, which is here. So it's 241.8. So all we do is we take our mass, which is 2.16, and we're going to divide that by 241.8. And if we stick that into our calculator, we should get the number of moles to be 8.93 times by 10 to the minus 3. Now it's really important. It did say that we've got to give our answer to three significant figures. So make sure that your answer is to 3 significant figures. If it's not, you won't actually get this mark. So it's really, really important that you read the question very carefully and make sure you give it to the appropriate number of significant figures. Okay, so question 2, which is to calculate the amount in moles of oxygen gas produced in this reaction. Now, there's two ways of doing it. I suppose the quickest way is the way which I'm going to show you first. Now, you can see here we've got the number of moles of oxygen. You can see we've got a 3 next to here. We know the number of moles of iron nitrate, which is this one here, iron 3 nitrate, because we've worked it out here. Now, you can see the ratio is 4:3, so we should have less number of moles of oxygen than we do compared to the iron nitrate. And because it's a 4:3 ratio, we can effectively multiply it. Effectively, it's like a 3/4 ratio. So if we turn that into a decimal, 3/4 as a decimal is 0.75. So if we take this number of moles here, which is 8.93 times by 10 to the minus 3, and then if we multiply that by 0.75, then we should get an answer. Let's bring our calculator in. So we put 8.93 times by 10 to the minus 3, multiply that by 0.75, and that should give us an answer of 6.6975. Now, if we do that to 3 significant figures, that should be 6.70 times by 10 to the minus 3. 6.70 times by 10 to the minus 3. Now, the alternative way, which is a little bit longer, is to take the number of moles here, and if we divide that number by 4, we can find out what 1 mole is, and then we can take the number, that answer we've just worked out, multiply it by 3 to find out the number of moles of oxygen, and we should get the same answer there. But again, this answer is in 3 significant figures, just again, we don't really need to be too fussy about that because it hasn't asked us in there, but we'll just keep it consistent. Okay, so if we look at the next question, now this question is a little bit bigger, and what it's wanting us to do is to calculate the volume in meters cubed of nitrogen dioxide gas at 293 degrees Celsius and 100 kilopascals, produced from 2.16 grams of iron 3 nitrate, and they've given us a gas constant, which is R, and that's 8.31 joules per Kelvin per mole. Now you can see they now give you a number here if you've been unable to work that out. So if you've not worked out the previous one, but obviously we'll just use the number that we've got there. Okay, and the first thing we need to do is we see this is to do with gases. So we're going to write our ideal gas equation. So I'm just going to put that there. PV equals nRT. Okay, and that's the equation that we need. And now you can see here we've got a lot of units here that are not correct. So for example, we've got temperature. We see they've given us it in degrees Celsius. That has to be in Kelvin. That's really, really important. And that's standard as well. It's a standard measurement that we do temperature in. And if we look at the other one as well, 100 kilopascals, according to the ideal gas law, a standard units for the ideal gas equation is pascals for pressure, not kilopascals. So we need to convert that into pascals as well. So that's what we're going to do first. So if we take our temperature, now to convert this into Kelvin, all we do is we take 0 degrees Celsius, and that in Kelvin is 273 Kelvin. And all we do is we add on this bit here, which is 293, because that's positive 293. So 273 plus 293. Now that should give us an answer of 566 Kelvin. Okay, so that's that one sorted. The pressure is the other one. So that's the P bit. Now pressure is in pascals. They've given us it in kilopascals. The K bit means 1,000. So that means our pressure has to be 100,000 pascals. That's really, really important. And actually, you get a mark for that just for doing them too. So converting it. So that's really, really important that you do that first. Okay, the next bit we need to work out, you can see we've got the T bit, we've got the P bit, we know the R bit because they've told us that, but the N we don't know. Now this is wanting us to work out nitrogen dioxide. So now to work that out, what we have to do is if we go back to our previous question, our previous equation, you can see here that we worked out the number of moles of oxygen, which actually turns out to be 6.70 times by 10 to the minus 3. And this represents 3 moles of oxygen here. So to work out the number of moles of nitrogen dioxide, you can see the ratio is 3 to 12. So that means that this number of moles is 4 times bigger than this. You can see that ratio there. 3 to 12 is the same ratio as 1 to 4. So what we have to do is take this number, which is the number of moles of oxygen, multiply it by 4 to get the number of moles of NO2, which we need in this equation here. So I'm just going to push that back up. So we're going to write the answer to that. So that's going to be 6.70 times by 10 to the minus 3. And we're going to multiply that by 4. And that should tell us the number of moles of NO2. So if we get our calculator, and we're going to put in 6.70 times by 10 to the minus 3, multiply that by 4, and that should give us a final answer, or the number of moles, as to be 0.0268 moles, and that's of NO2. Brilliant. Right, so now what we've got is we've got temperature, we've got pressure, and we've got N. We also have R as well, so we've got everything we need, and actually you get your second mark actually comes in with that one there. So now what we have to do is we have to take this equation here and we have to work out the volume in meters cubed, and that's already in the standard unit anyway. So that's really, really simple. All we do is we rearrange it and we get V equals N R T over P, and if we put our numbers in, that should be 0.0268, which is our number of moles of NO2, times by 8.31, multiply that by 566, that's our temperature in Kelvin, and we're going to divide that by the pressure, which is 100,000, and that's in pascals. Now, if you're not sure on how to rearrange this formula here, I have done a video on rearranging the ideal gas equation. So we just click on the link that appears on the screen, and you can have a look at that if you're not sure how to do that. So actually just writing this expression here gets you another mark. So it's really important that you write your expression, really, really important, or you show your numbers that's been substituted in the expression. Now, if we get our calculator and if we work out our answer here, so that's 0.0268 times by 8.31 times by 566, and if we divide that by 100,000 pascals, we should get an answer of 1.26, and again we'll keep it to 3 significant figures, times by 10 to the minus 3. So I'm going to put our answer on there. So volume, or V, will equal 1.26 times by 10 to the minus 3 meters cubed. And that's obviously your final mark. So you get 4 marks for that. So really important that you convert your units. Temperature's always got to be in Kelvin. Pressure's always in pascals. Obviously moles is just in moles. And your volume has also got to be in meters cubed as well. So that's really, really important that you get them units correct there. Okay, so if we move on to the next part, question 2. Pull that down. Okay, right, so we've got the first question. It says, suggest the name of this type of reaction that iron 3 nitrate undergoes. So I bring this sheet back just quickly, just to show you. So you can see here that the equation shows iron nitrate, and it's not reacting with anything, but it is forming 3 products. Now, when you see that, that's a classic sign of decomposition. And because we're producing a gas, this will be thermal decomposition, and it's heated, so it tells us. So this is effectively thermal decomposition. So look out for one reactant on the left producing a lot of products. That's a classic sign of decomposition. Okay, so we're going to write that down in there. So that's going to be thermal decomposition. All right, okay. And 2C, which is the last bit for question 2, says suggest why the iron 3 oxide obtained is pure, assume a complete reaction. So again, if I bring back our equation, you can see here that we've got why iron 3 oxide is pure. So you can see there's our iron 3 oxide. Our other products are actually gases, so these will escape, and it will only leave this behind, which is a solid. So really, you need to be looking at the state symbols to help you with this one. And so that is your final answer. So the answer is actually other products are gases. And so they can escape easily. All right, okay. So you can see that just gets 1 mark for that as well. So you can see, really, really important. The ideal gas equation is the one that you really have to remember. You get the bulk of the marks there. Make sure you look at the equations really carefully that they give you. They might give you some ones that are a little bit obscure, but failing that, you should be okay. And as you can see, you get a total of 8 marks for that question there. So that's it. On to the next question. Okay, so this is question 3, and question 3 is a little bit of a mixed bag. It contains topics such as bonding, and it's got a little bit of electron structure and configuration as well. So we're going to start with the first question here, and you can see here that it says that nickel is a metal with a high melting point. State the block in the periodic table that contains nickel. So what we do, if we bring in our periodic table here, we can see that nickel is here, and this is the D block of elements. So these two are S blocks, which are here, and these two as well. These are P blocks, and so these ones are D blocks that sit in the middle here, and you can see nickel sits in there. So nickel is a D block element. So we're just going to write that down on our sheet. So this is D block. Okay, right. And the next one, it says, explain in terms of structure and bonding why nickel has a high melting point. Now, nickel is a metal, so therefore it will have metallic bonding. And so you need to understand the structure of metallic bonding. And the first point, you can see there's 2 marks here that's available. So we need to first say that there are positive metal ions. And what we have with these positive metal ions is we have a strong attraction. So I'll put that on there, strong attraction. And this is between a set of delocalized electrons. So I'll put a C of delocalized electrons. Now the words which we are looking for, what the examiner's looking for, I'll just put this on here. And electrons are negatively charged. So put on there, negatively charged. Okay, and it's a strong attraction between the sea of delocalized electrons that are negatively charged and the positive ions. So the key parts here that they're looking for in the exam is they're looking for the word strong attraction, and that would actually get you the first mark. And the strong attraction is between a set of delocalized electrons, and this is the attraction between the negative charge of these and the positive ions. So actually, there's only 2 marks available for this question, and the marks come in for the strong attraction between the sea of delocalized electrons, and that is really, really important, that word, which is delocalized electrons. Okay, so if we look at the next question, which is 3A part 3. Now what it's asking us to do is to draw a label diagram to show the arrangement of particles in a crystal of nickel, and in your answer include at least 6 particles of each type. And you can see here that we've got 2 marks that are up for grabs. So it does say a labeled diagram, and it says 6 particles. So this is effectively trying to illustrate what we've described up here, but we're only interested in the particles. So we've drawn 6 particles, and these particles have a positive charge, as we described earlier on. Now there's 2 marks available for this, and so what we need to say is that these, you actually get 1 mark for putting positive charge, so that's the labelled part. You've labelled the particles with the positive charge, and actually the second mark comes in for the rearrangement, or the arrangement of the positive ions. So these are in a what we call a regular arrangement, and that's really, really important. Okay, so there's regular arrangement where they're in rows, and that's really crucial. You don't need to bother with the electrons here because it did only say that we need to draw 6 particles, and no, not worried about the electrons. You won't lose marks if you put the electrons in, but we don't need to put them in. Okay, so if we look at the last question here on this page, which is 3A.IB, it says explain why nickel is ductile. That means it can be stretched into wires. This can be a little bit tricky if you don't really understand the structure of metals, but ductile means it can be stretched into wires. Now what that means is that these layers here in this metal can actually slide over each other, and that means it can be drawn into cables. So I'll do an example. You might have two, for example, you might have 2 layers here, and effectively we can stretch these into wires because we can pull them, slide over each other, and we can stretch them into one long wire like that. So that's why we can do it. So it says explain why nickel is ductile. It is 1 mark, so all we need to say is that the layers can slide over each other. Okay, right, so there's your answer there. So this is just 1 mark. Okay, so if we go on to the next page, question 3 continues, over onto the next page. And there we go. Okay, so if we look at the first question on this page, which is 3B, says nickel forms the compound nickel 2 chloride, or NiCl2, and it's asking us to give the full electron configuration of Ni2 plus ion. So we're looking at the ion here. Now you've got to be really careful with this. So you can see here, so if I bring the periodic table and just nudge that up a little bit, you can see the question. Okay, right, so what we've got is we have nickel, which is here, but what we've done is we've taken 2 electrons away from it because it's Ni2 plus. So what we're going to do is we're going to start from the top here, and it does say the full electron configuration, so we do have to write the whole lot. So here's the first one. We'll start from here. So there's 1s2, so I'm just going to put that there. Big 1, little s, and a 2 in a subscript. That's really important that it's written like that. And then we go 2s2, because it's the second one. If we keep on going, this is 2p and there's 6. So we keep on going like that. 2p6. And then we go on to the next one, which is 3s2. And then we keep going. So this is us here. And then we go 3p6. Right, now this is where we need to be really careful here. You can see that to get to nickel, we have 4s2. And then we have 3d 8, which is here if it was nickel element. However, 2 electrons have been removed. Now, when we remove electrons from transition metals like this, then we have to remove electrons from the 4s orbitals first. So because we're removing 2 electrons, the 4s orbital is taken away first, and that leaves us with the 3d8 electrons. So actually after this, we just have 3d8, and we have no 4s2 orbitals because we removed them electrons first. And that's really important. You don't have 4s2 3d6 because you remove the electrons from the 4s orbital first. So it's really, really important that you understand that. That's a little bit tricky there. Okay, and if we just go on to the last question, and this is just a classic balance in the equation, it's also added a little bit extra as well, where we have to identify one substance that could react with both gaseous products. So we're going to balance this thing first. Now, if we look, we're looking for simple multiplication. So you can see here, if I start from this side, you can see that this molecule we have hydrogen, we have 6 lots of H2. This is what we call water of crystallization, .6H2O. And we have 12 hydrogens. Now, if we look on the right, the only molecule on the right-hand side with hydrogen is this. So, therefore, we must have a 12 in front of there to make it balanced. And so that's our first move, is to add 12 on that side. And that gets that one sorted. Okay, so now if we look at this, obviously this has increased the number of chlorines that we've got on the right hand side. So we've got 12 chlorines there, and we've also got 2 chlorines there. So that gives us a total of 14 chlorines. Now, if we look on this side, we have 2 chlorines there, we have 2 chlorines there. So that's a total of 4. So that means what we need is a 6 over on that side. And that effectively gives us 12 and 14 chlorides over on this left hand side there. Again, we don't want to put a number here because we've just balanced our hydrogens according to this, and this is the only molecule with hydrogen in, so we don't need to put our number there. It has to go here to balance our chlorines. Okay, so now once we've done that, you can see that we actually now have an imbalance in sulfur. We've got 6 sulfurs on this side, and we've only got 1 on this side. So our next move is to put a 6 there, and as you can see, that is now finally balanced. So that gets you the first mark. And then the last bit is we have to identify one substance that could react with both gaseous products. Now, the gaseous products are these two here, so it's sulfur dioxide and HCl, and you should know that these products are acidic gases. So anything that will react with acidic gas, such as an alkali or a base. So, for example, you could have calcium carbonate, for example. You could have calcium oxide as well. You could have a traditional base such as ammonia, NH3, or anything like sodium hydroxide would do as well. But really what we're looking for here is any alkali will suffice here, I suppose. You could even have water if you wanted to, because these two would react with water to form acidic solutions. So if you've done all of them correct, you should get a total of 9 marks. And so let's move on to the next question. Okay, so this is question 4, and question 4 is mainly to do with the topic of bonding. So we'll start with the first question, which is 4a, and it says ammonia gas readily condenses to form a liquid when cooled. Name the strongest attractive force between 2 ammonia molecules. Now, ammonia is NH3, and therefore the strongest attractive force, or intermolecular force in this case, would be hydrogen bonding. So that's what we're going to write there. Now, hydrogen bonding is a bond, or there's an intermolecular force, should I say, that actually only occurs between the hydrogen and the 3 most electronegative elements, or some of the most electronegative elements in the periodic table, which is nitrogen, oxygen, and fluorine. So if I bring in the periodic table here, you can see that it's actually these 3 here. It's just these 3. So anything with hydrogen NOF or any molecule with that in will interact via hydrogen bonding. Okay. So the next question, which is 4.2, effectively wants you to draw a diagram to show this. So it says draw a diagram to show how 2 ammonia molecules interact with each other in the liquid phase. Include all partial charges and all lone pairs of electrons in your diagram. So what we're looking for is 2 ammonia molecules, and so that's what we're going to draw. And we need to show how they interact. We need to include all partial charges and all lone pairs as well. So they're really, really important. So that's what we're going to do. So we'll draw our nitrogen and our 3 hydrogens, and we'll draw another one somewhere up here. Now, ammonia has a lone pair of electrons, and so I'm just going to represent these as 2 little crosses. So that's the first bit. And then what we have to do is then we have to show our partial charges. Now, nitrogen is electronegative, so we're just going to put delta negative on there, and the hydrogens are delta positive. And it does say show all of them, so you do have to put the little delta negative and delta positives next to all of the elements that you've drawn, because it does say that. So if you miss one of these out, you'll actually lose a mark. So that's really, really important. We've also put our lone pairs, they're the only two lone pairs on there, and we need to show how these molecules interact with each other. So what we're going to do is we're going to draw an interaction. Now the interaction must be between a lone pair of electrons and a delta positive hydrogen. So normally it's good to represent the interaction with a dotted line. Now as long as it goes from the lone pair to the hydrogen, then that's all we're really fussed about. Okay, so the marks obviously come into labeling our lone pair. So there's the first mark. The second mark is our partial charges. So that's the second mark. And the third mark comes into drawing your hydrogen bond interaction. Now, even though it's called a bond, it isn't. It's actually an intermolecular force, which is just an attraction between the molecules, not actually physically bonding, and that's why we've drawn it as a dotted line. Okay, so there's your 3 marks. If we go on to the next question, which is 4b, now it states that we need to, well, the question's asking that says ammonia reacts with boron trichloride to form a molecule with the following structure. So you can see here that we've got our boron trichloride here, and it is reacted with the ammonia, and we have different bonds that's in existence here. So it says state how the bonds between ammonia and boron trichloride is formed. Now what it's looking for is it's actually talking about this bond here. And this bond is called a dative covalent bond or a coordinate bond. And coordinate bonds is where we have a lone pair of electrons being donated from one molecule to another. So in this case, what we need to say is we need to put a lone pair of electrons. And this is on the nitrogen, because that's where it's going from. And effectively this is donated to boron. You can say BCl3 if you want, it doesn't really matter to be honest, but the key word there is that it's donated and we have a lone pair of electrons, and it's really important that you're specific and you say where it goes from and where it goes to. It's no good just saying lone pairs are donated from nitrogen, because you won't get the marks there. So it's really important that you say where it goes from and where it goes to. All right, okay, so let's look at the next question. Okay, so let's pull that down so we can see it. Okay, so question 4c. We have table 3 shows the electronegativity values of some elements, and you can see that we have a range of elements and we have their electronegativity value. So the higher the number, the more electronegative the element is. And they're asking for a definition or what the meaning of the term electronegativity is. Now this is something that you really have to remember. So we're going to write this down here. And so this is the ability, or you could say power, of an atom, or you could say nucleus, to attract electrons towards itself and then in a covalent bond. We only get this electronegativity in molecules with covalent bonds. So that's really, really important. Now, this is a 2-mark question. So the marking points is effectively the attraction of electrons. So that is your, So that is your first mark, which is there. And then your second mark is the covalent bond bit, and that's really, really important, is that we say that it's attracted in a covalent bond. So that is your second mark, which goes there. Okay, right. Then if we go into the next question, and this is asking for a formula of an ionic compound that is formed by the chemical combination of 2 different elements from table 3. Now this has a variety of answers. It is just asking for an ionic compound. So generally this means that we have a metal and a non-metal. So as you can see, we only have one metal in there, and this is lithium. So lithium has to be involved in this, and you could effectively bond it with any of the other nonmetals. But what they're looking for here is the correct formula. So you might have something like lithium fluoride. You might have lithium oxide, Li2O, or you could have something like lithium hydride, which is LiH, etc. So you could have any of them, or you could have a carbide as well, if you like. Now, the key thing is the formula here. Lithium is in group 1, so if I pull in the periodic table. Okay. So lithium is in group 1, and we said fluorine, which is in group 7, which is over here. Let's bring it into focus. And you can see this is a +1 and that's a -1, so you only need 1 lithium and 1 fluorine, whereas the one with oxygen, you need this needs effectively 2 electrons to get a full outer shell of electrons. So it needs to bond with 2 lithiums because lithium can only give up 1. So that's why it's Li2O. So what they're looking for is the formula here mainly, and your understanding of ionic compounds. And the last question, which is for C, part 3, it has to suggest the formula of the compound that has the least polar bond and is formed by chemical combination of 2 of the elements from table 3. So all we have to do, if I just bring that down there, is we look at the elements and we're looking for the smallest difference. You can see the smallest difference is between these two. It's only a difference of 0.1. So this is boron, which is in group 3. If I bring in our periodic table again, now it is there, so it's in group 3. And hydrogen obviously only has 1 electron and only needs 1 to gain a full shell. So the compound, the name of the compound is BH3. And the reason why is because we only have a difference of 0.1 from that table. So that's relatively straightforward. And that is the smallest difference. And that is question 4. So on to the next question. Okay, so this is question 5, and question 5 is mainly to do with alkanes. It also has a little bit of bonding in there as well, and a little bit of nomenclature, but it all kind of comes together anyway. Okay, so let's make a start. So it says some oil-fired heaters use paraffin as a fuel. One of the compounds in paraffin is the straight-chain alkane dodecane, C12H26. Give the name of the substance from which paraffin is obtained. State the name of the process used to obtain paraffin from this substance. So paraffin is, as it says, is used as a fuel, and we get these as a hydrocarbon as well. So we get these from crude oil. So that's just the one you need to remember. And the process, what we extract it, is fractional distillation. And again, that's something that you just need to know. So I'll put that on there. Fractional distillation. Okay, right. So on to 5b. The combustion of dodecane produces several products. Write an equation for the incomplete combustion of dodecane to produce gaseous products only. So this key word here, incomplete. And the other one as well is that it says gaseous products. Now there's 2 main products that you need to know for incomplete combustion. One of them is soot, which is just carbon, and the other one was carbon monoxide. Now, the only one that is gaseous out of them is carbon monoxide. So we need to write an equation that involves that. So we're going to start with dodecane, which is C12H26. And we're going to react this with oxygen. So we'll just stick our oxygen in there as well. And we have to produce a gaseous product, and that's got to be carbon monoxide. And we always produce water in these products as well. Now, the easiest way to balance this equation is if you look, we have 12 carbons on this side. The only molecule on the right with carbon is this one, so we must have a 12 that goes on there. The next thing to look at is also the number of hydrogens. You can see here we've got 26 here, and because we've got H2 there, that's got to be a 13, which goes there. And then all we do is balance up the oxygens, so that leaves us with 12.5 over on that side, and that's how you do it. Okay, so 5c, which is this one here, it says oxides of nitrogen are also produced during the combustion of paraffin in air. Explain how these oxides of nitrogen are formed. Now, this is a 2-mark question, so we need to give 2 points. Now, it's talking about nitrogen and oxygen. This is the combustion of paraffin in air. Now, what is found in air is nitrogen. The vast majority of air is nitrogen. So when we heat that up, we actually form the nitrous oxides or the nitrogen oxides. So we need to start the sentence really with saying that nitrogen and oxygen and these react together. And like I say, these come from the air. So there's your first marking point. And this will only happen, obviously we have nitrogen and oxygen in the air now, but they're not reacting. But if we heat them up, which will be true in a paraffin heater or even a car engine if it's in a car, with the heat there will actually be enough energy for these two to react. So this happens at high temperatures. Happens at high temperatures. All right, so let's just assign the marks because it is 2 marks. So you get 1 mark for saying that they actually react together, which seems pretty obvious. And your second mark then comes in where we say we need the heat as well. So they're the marking points that we're looking for. All right, so if we move on to the next question, a little bit further up. So 5C part 2. Write an equation to show how nitrogen monoxide in the air is converted into nitrogen dioxide. Now they'll do this quite a bit where they'll tell you exactly what's being converted. So we need to write the formula of nitrogen monoxide and we need to write nitrogen dioxide. Now you only need to put in the missing bit. Now we're just going to write nitrogen monoxide here. That's just NO. And it's converted into nitrogen dioxide. Now the difference between these two is oxygen. So we're going to write oxygen here. And that's going to form nitrogen dioxide because we've gained the extra oxygen, so we have to react it with oxygen to get there. And then all we have to do is just balance it up. So we're just going to put 2 there and a 2 there, and that makes it balanced. Okay, and 5C part 3, nitric acid, which is HNO3, contributes to acidity in rainwater. Deduce an equation to show how nitrogen dioxide, which is this chemical we just worked out, reacts with oxygen and water to form nitric acid. So they've actually told you the equation here, which makes it a little bit easier. So we're going to write nitrogen dioxide, which is going to be NO2, and that's going to react with water and oxygen, because they've told us that, and they've even told us that it'll form nitric acid. They've even given us the formula for that as well. So you literally write down the equation like that. Now obviously you're not going to get the mark for just writing that equation down because they've told you that. So what we have to do is we have to balance this equation. So again, what we're looking for is the making sure that our nitrogens and hydrogens all balance. So what we do is we put a 4 there, and we put a 4 there on that side, and then we put the 2. So that's just a simple case of balancing the equation. So make sure you get lots of practice at that because they will be expecting you to balance equations, obviously, because it's a chemistry exam. All right, okay. So let's move on. It's quite a big question, this one. There's a lot of marks up for grabs. Okay, so if we drag it down just so we can see the top question. Okay, so we're still talking about dodecane, C12H26, and this can be cracked from other compounds, or to form, other compounds. Give the general formula of the homologous series that contains dodecane. Now, the homologous series is the family that this belongs to. Now, this is an alkane, so that's the family it belongs to, and that will have a generic formula that allows us to work out any formula of any alkane. And you really do need to remember this one. This is just CnH2n plus 2. Now what this means is that for every carbon atom we have 2 lots of hydrogen and then we add a 2 onto there. So you can see, you can try it in the formula, C12, so if this n was 12, double 12 gives us 24, plus the 2 gives us 26. So you can see that that general formula fits with that equation there. Okay, so 5D part 2. Write an equation for the cracking of one molecule of dodecane into equal amounts of two different molecules, each containing the same number of carbon atoms. State the empirical formula of the straight chain alkane that is formed and name the catalyst. So they're wanting three things here, and they've given us a little bit of structure to help us out here. So the first thing is we need to write our equation, and this is the cracking of one molecule of dodecane. So we're going to write dodecane here, and dodecane is C12H26. Now, crucially, it says equal amounts of two different molecules, each containing the same number of carbon atoms. So what that tells us is that we just have to divide this carbon, or these number of carbons, into two different groups. So each molecule must have six carbons in total. So one of them, it says, we've been told is an alkane. So if we use our general formula, we should come up with C6H14. And we know the other molecule's got to have 6 carbons as well, because it says equal amounts. And then we just count the number of hydrogens left, and we'll see that we only actually have 12 hydrogens left. So this is an alkene. So we form an alkane and an alkene. All right. So the empirical formula for the alkane, this is the alkane here. This is hexane. The empirical formula is just the simplest whole number ratio of atoms in the molecule. And so if we effectively cancel this down, the simplest ratio would be C3H7. Okay, and finally the catalyst that allows this to happen. So this is cracking, and the cracking process needs a zeolite catalyst. It's like a honeycomb structure. Looks a little bit like a crunchy bar, if you know what one of them are. And or you can use something called aluminosilicate. So they will accept that as well. All right, okay, so you can see we've got 3 marks there just for this. And again, it's something that you really need to know. If you didn't know this bit in particular, it's either you know it or don't know it. The rest of them you could kind of work out from the question there. It gives you a little bit of hint. Okay, so if we look at the last question here, which is on this page, which is 5D part 3, it says explain why the melting point of dodecane is higher than the melting point of the straight chain alkane produced by cracking dodecane. So we're basically comparing this, which is dodecane, and this, which is hexane. So we're going to compare these two and say why this one has a higher melting point than this. Now, there's 2 marks up for grabs here. So we need to first of all state that one of the molecules is bigger, and in this case, it's dodecane. So dodecane is a larger, or you could say longer molecule, or has a larger surface area, anything like that. I'll just put larger. Okay, so dodecane is a larger molecule, and so the crucial thing is that the only intermolecular force, it's intermolecular forces that in simple molecules that govern the melting point. The only intermolecular force between any of these is van der Waals forces. There isn't any dipole-dipole, and there isn't any hydrogen bonding because we don't have any serious electronegative elements in there. So the strongest one is van der Waals, and basically the bigger the molecule, generally the higher the van der Waals, and therefore the higher the melting point. So we first of all stated that dodecane is the larger molecule. So I'm going to put, so you have more, or you could say stronger, van der Waals forces between the molecules. Right, now this last little bit is really, really important. I'll just highlight where the marks are first though. So this is larger molecule, that gets you the first mark. And the second mark is you have more van der Waals forces. So I'm just going to underline that bit there. Between the molecules. Now if you miss this bit out here at the end, you actually don't get the second mark. So I'm just going to mark that up. There's the 2 marks. it's really important that you specify exactly where these forces are, and the forces are between the molecules. They're a little bit like bar magnets, and basically the bigger the bar magnet, the more energy you need to do to pull that apart. So, so if we just like take an example, so here's 2 pens. You've got 2 alkanes, and in between the 2, you'll have weak forces that sit in between these 2 here. And obviously, the longer the molecule, the more forces you've got between the molecules, and it means you need a lot of energy to pull them apart and turn them into a gas that allows them to move around freely. So that's the idea behind it anyway. Okay, so if we move on to the final part of this question, told you it was a big question. Okay, so this is 5 part E. So get that in the camera so you can see it. Okay, so it's asking us to give the IUPAC name for the following compound and state the type of structural isomerism shown by this compound and dodecane. Right, so we need to give the IUPAC name of this. Now, the crucial thing is with naming is you've got to find the longest hydrocarbon chain first. And for simplicity, we're just going to pick this middle one here. So we're just going to put the numbers on there. So that's carbon 1, it's carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So this is going to be hexane. You can see there's a long hydrocarbon chain here. And I've started the numbering on the right and not on the left because we have these groups which we need to name needs to be attached to the lowest possible number. So if I numbered it from this side, 1, 2, 3, 4, 5, 6, you can see that these groups will be on the 3rd, 4th, and 5th carbon, which is a lot bigger than if we numbered it here, which would be the 2nd, 3rd, and 4th carbon. So the crucial rule with IUPAC is that you always make sure that you number it so you get the lowest numbers. So these groups are attached to the lowest numbers possible. Okay, so then we just need to name this molecule. Now this is quite a big molecule, so we've got a lot going on here. Here's our functional groups hanging off this main kind of arterial molecule, which is the 6 carbons there. And you can see here that we have 2 methyl groups, 2 methyl groups, and 2 methyl groups. So all these are methyl. And according to IUPAC, we say where they are first. So we've got 2, because we've got 1 there. And we've got 2 more on the 3 as well. So that's going to be 3, 3. We've also got 2 on the 4th carbon as well. So that's going to be 4, 4. Hyphen, and we always separate numbers with a comma and numbers and letters with a hyphen. So this is going to be hexa because we have 6 of these. 1, 2, 3, 4, 5, 6. Methyl. And the long chain is hexane. There you go. So this is 2, 2, 3, 3, 4, 4, hexa, methyl, hexane. So this bit always tells us how many of them we have, and this tells us where they are situated on the molecule. And the type of structural isomerism, as you can see, you need to know these really, the types of isomerism. This one is chain isomerism, and we are comparing it to the type of structural isomerism shown by this compound in dodecane. And you can see compared to dodecane, which is just one long hydrocarbon chain, this chain has been broken up and we've taken some of the carbons and bolted them on as branches from the molecule. So we call this a chain isomerism. Okay, and the final question for the final part of this question, which is 5F, dodecane can be converted into halododecanes. And it's asking us to deduce the formula of a substance that could be reacted with dodecane to produce 1-chlorododecane and hydrogen chloride only. So the molecule that we use here, because it's chlorine, it has to be Cl2 or chlorine. Now it's really important, it does say the formula, so you can't write chlorine, you've actually got to write the actual formula for it there, which is going to be Cl2. But yeah, if you get all that, obviously you get 16 marks, which is a really good, decent number of marks in this Unit 1 paper. Yeah, on to the next question. Okay, so this is question 6. You can see here that we're now at the section B. Section B is the part of the exam which is a little bit less structured. and requires you to do a little bit more thinking. It is the most difficult part, or is designed to be the most difficult part. Of course, it's only difficult if you don't know the answer. So hopefully by looking at this, you'll be able to see that it's actually not too bad as long as you read the questions very carefully. Okay, so this question is, in this case, question 6 is actually amount of substance. So it's all calculations. There's big marks to get here. You've got to make sure you read the question carefully. So we'll start with this one. Calcium phosphate reacts with aqueous nitric acid to produce phosphoric acid and calcium nitrate as shown in the equation. And you can see they've given us the equation there. A 7.26 gram sample of calcium phosphate reacted completely when added to an excess of aqueous nitric acid to form 38.0 centimeters cubed of solution. Calculate the concentration in moles per dm cubed of phosphoric acid, which is this here, in this solution, and give your answer to 3 significant figures. So this is really, really important. All our calculation, all our numbers are going to be to 3 significant figures. Okay, so the first thing we have to do is, because we're working out a concentration, we need to work out moles. And there's a saying that I like to use, which is, if in doubt, calculate moles. Because once you know the moles of something, you can work out the moles of anything else in this equation. And from the moles, you can work out mass, you can work out MR, you can work out concentration, you can work out volume, you can work out loads of things from the moles. So that's the first thing we're going to do, and that's how we're going to start this question here. And that's what the examiners have aligned on you to know how to start it. So you can see that we've got a mass of calcium phosphate here. Now, because we've got a mass, we can work out the moles of calcium phosphate, providing we have the MR. So what we're going to do is work out the MR of calcium phosphate first. So I'm just going to write that there. So MR of calcium phosphate, which is PO42. So if you work out the MR, and we're going to keep this to 3 significant figures, this should give an MR of 310. Okay, so once we've worked out the MR, because we know the mass, like I say, we can work out the number of moles. So I'm just going to write that there. So this is the moles of calcium phosphate, PO42. Okay, and so the number of moles is the mass in grams divided by the MR. So put that there in grams. So the mass we know is 7.26. 7.26, and we're going to divide that by the MR that we've just worked out, which is 310. Notice all our numbers are 3 significant figures as well. And that should give us a final answer. If we bring the calculator over, and that should be 7.26 divided by 310, and that gives us an answer of 0.0234. We only need it to 3 significant figures, so I'm just going to put that there, 0.0234. All right, now, so far we've got ourselves 2 marks, 1 mark there and 1 mark there. So we work out the number of moles of this. Now, because we know the number of moles of this, we need to work out the concentration of this, which is phosphoric acid. So we can work out the number of moles of this next by using our simple ratio. And then once we've got the number of moles of that, we can then work out the concentration. So you can see that the moles are so important here. So we're going to work out the number of moles. I'm just going to nudge that up a little bit. So we're going to take this number here. We're going to do, I'll just write it here. So moles of H3PO4, and that should equal 0.0234. Multiply that by 2, because we're wanting to work out, because we've got a 1 to 2 ratio, and we should get an answer of 0.0468. Because you can see we've just doubled all the numbers in there. Okay, so now we know the moles of phosphoric acid. We then need to work out the concentration. So the concentration, which we'll write here, so the concentration is the number of moles divided by the volume, because it's moles per dm cubed. That's the units of concentration. But the volume, like I say, has to be in decimeters cubed. So put that there. Okay, so what we need to do now is we need to work out the volume in decimeters cubed. We have a volume in centimeters cubed, so we need to convert that into decimeters cubed. And it's really easy. We just take the number of moles first, which is this. And so the number of moles is going to be 0.0468. We're going to divide that by the volume. Now the volume of this was 38.0, but this has to be in decimeters cubed. So all we're going to do is I'm just going to put times by 10 to the minus 3 on the end of that number there. And effectively what that means is it turns this, effectively that means divide by 1,000. And it turns this centimeters cubed into decimeters cubed. And so if you put that into your calculator, which is what we'll do now. So this is going to be 0.0468 divided by 38.0 times by 10 to the minus 3. Put that on our calculator, and we need it to three significant figures, 1.23. And so we're going to write that there, 1.23, and this is in concentration. So this is moles per decimeters cubed. Okay, so let's just quickly show you where you get the marks for this. So you get the first mark for calculating the MR of calcium phosphate first. You get the second mark for then working out the number of moles of calcium phosphate. You then work out the number of moles of phosphoric acid for the third mark. You then substitute the numbers. You write the equation to work out concentration. So you actually get a mark for just putting in the numbers there. And then your final mark obviously comes in with your answer. So that's 5 marks. And the saying there really is, if in doubt, work out the moles. And the moles you can work out so many things from the moles. So it's a little bit like signposts. So this is like the center of chemistry is moles. So it's really important. Okay, so if we look at the next question, I'll just push that up there. Calculate the percentage atom economy for the formation of calcium nitrate in this reaction and give your answer to 1 decimal place. All right, so what we have to do is percentage atom economy of calcium nitrate. So if I bring this down here, just so we can see it, you can see it, we've got calcium nitrate here. This is the useful product. Now, the percentage atom economy is the mass of atoms in the useful product, which is this, divided by the total mass, or MR, of the reactants. And that's including the number of moles as well. So if we work out the MR of calcium nitrate, and then we multiply that by 3, because we need to take into account 3 of them, we should have an MR. So we should have an MR of 492.3, and this is to 1 decimal place. So we're going to just keep our number to 1 decimal place. We're going to divide that by the total MR of the reactants, which should come out at 688.3. And we're going to multiply all that by 100 because it's percentage atom economy. And if I bring the calculator over, do 492.3, divide that by 688.3, times that by 100, and we should get 71.5%. And again, it's to 1 decimal place, so we round that up. So that should give us 71.5%. So this is for 2 marks. So we're going to see where the marks come from. So the first mark comes in for this equation here, and the second mark is for your percent. So there we go. So you've got yourselves 5, 6, 7 marks so far already for this one. Okay, so let's continue on with question 6. So move that one out of the way. Right. So we have 6b, and it's asking us to write an equation to show the reaction between calcium hydroxide and phosphoric acid to produce calcium phosphate in water. This is quite a tricky equation. There's a lot going on here, and you really need to know your chemical formula for this. So we're going to start with calcium hydroxide. Now the formula for calcium hydroxide is CaOH2. Now we know that because calcium, if I bring over the periodic table, now calcium is actually in group 2, as you can see on there. And the hydroxide, we have 2 of these because OH minus, hydroxide is OH minus. So I'm just going to Move that out of the way. Okay, so if I write the ions just at the top here, so we have calcium is 2 plus, and that means our OH is obviously minus. So we need 2 of them to balance out the calcium 2 plus. Okay, so this is going to react with phosphoric acid, because that's what it said. Now, they told you the formula for phosphoric acid, so that's not too bad. H3PO4. Okay, and that's going to form a product called calcium phosphate. Now, calcium we know has a 2 plus charge, so I'm going to put that there. And phosphate actually has a 3 minus charge. So what I'm going to do is I'm going to write Ca3. I'll write the formula first. Okay, so if I show you how I've worked that out though, phosphate hydrogen we know is +1 for each hydrogen. Because we have 3 of them, that means the PO4 bit must be 3 minus. Now, if I combine that with that, you can see that we need 3 calciums, which are 2 plus, to balance out the phosphates, but you need 2 of these. So if I have 2 of these, that'll take it up to -6. And if I have 3 of these, that'll take it up to +6. So that's how I know calcium phosphate is Ca3PO4 2. And that's really important. You've got to be able to work them out. And obviously, we produce water as well as a byproduct. Okay, so now all we have to do is just balance it. You can see we've got a 3 there, so we just stick 3 on this side over there, and that's obviously knocked some other things out as well. So we're just going to put 6 here to balance out our water, and then we put 2 there, and that should be it balanced. So you have to do quite a bit there to just get 1 mark, but you know, 1 mark is better than nothing. Okay, so make sure you know these your ions as well. That's really important. That's what they're examining you on there. Okay, so if we look at the last part to question 6, you can see here we've got calcium dihydrogen phosphate can be represented by the molecular formula CaH2PO4X, where X is an integer. It says a 9.7 gram sample of calcium dihydrogen phosphate contains 0.17 grams of hydrogen, 2.59 grams of phosphorus, and 5.33 grams of oxygen. Calculate the empirical formula and hence the value of X, and we have to show our working as well. So what we're going to do is we're going to set out our table. Now, when you're working out the empirical formula, then what we have to do is we put our elements at the top of the table. So it's like a table. So we're going to put calcium, we're going to put hydrogen next, we're going to put phosphorus next, and then we're going to put oxygen next. So what we have to do is work out the mass of these 3 here. So we're just going to put, well, the mass has been told. So we know there's 0.17 grams of hydrogen. So we're going to start with that first. 2.59 grams of phosphorus, and we have 5.33 grams of oxygen. So now what we have to do is work out the mass of calcium. Now we've been told the total mass of this substance. So what we're going to do is we're going to bring in our calculator. We're going to add up these ones first. So I'll just notice that down there. So it's 0.17 plus 2.59 plus 5.33, and that gives us 8.09. Now, if we subtract that, 9.76 minus 8.09, then we should get 1.67, and that is the mass of our calcium. So I'm going to put that over there. All right, okay. So once we've done that, we then need to divide, both of these by their MR, or AR, should I say, because it's atomic mass. So for calcium, it's going to be 40.1, and for hydrogen, it's 1. For phosphorus, if you look at the periodic table, it should be 31, and for oxygen, it should be 16. Now, if we put all of them numbers into the calculator, and we're effectively working out the number of moles. So we're going to do 1.67 divided by 40.1, and that should give us 0.042. which I'm going to write there, 0.042. And then if we work out this one's just going to be 0.17, because that's just divided by 1. This one is going to be 2.59 divided by 31, and that's going to be 0.084. So we're just going to put that there, 0.084. And then if we do the final one, which is this one here, that's going to be 5.33 divided by 16, and that should give us 0.333. And if we just keep on going, so this is going to be 0.333. Okay, so we're keeping all this to 3 decimal places in this case here. All right, okay, so what we have to do is, once we've worked out, this is effectively the number of moles, that's all we've worked out here. Once we've done that, we then need to divide all of these numbers by the lowest number of moles. So the lowest number of moles is this one here. So we're going to divide that by 0.042. And we're going to divide all of them by 0.042. There we go. Okay, now if we put that into our calculator, obviously we get this one as 1. This one, the H bit, is going to be 0.17 divided by 0.042. And we get, if we round that, that's just going to be 4, as you can see. I'm just going to write 4 there. Okay, and if we go on to the next one, which is 0.084 divided by 0.042, that gives us a nice round number of 2. And this one is going to be 0.333 divided by 0.042. And that should, if we round that up, that should give us a number of 8. Okay, so our empirical formula effectively will be this. So it'll be Ca, and then we've got H4P2O8. Now, what we have to do is then we have to work out how many of the phosphate bit, the H2PO4 bit, do we have. Now, if I just segregate that and put that into a bracket, you can say that normally PO4, well, the hydrogen phosphate, sorry, is H2PO4, but you can say here we've got H4P2O8, so you can see effectively what we've got is we've doubled this compared to what the original one was. So therefore the value of X, which is there, X will actually equal 2, because we've got double the amount. So in terms of the marking criteria for this, you actually get 1 mark for working out this top bit here. You get 1 mark for actually working out the number of moles, which is this bit here. You get 1 mark for working out your empirical formula, which goes there, and then you get 1 mark for showing that actually the value of X is 2, and that's an integer, which means it's a whole number. But yeah, as you can see, a little bit tougher, and you've really got to watch out for them. But there's a saying, if in doubt, work out the moles, and that should get you the full 12 marks. On to the next question. Okay, so this is the final question of the 2014 summer paper for Unit 1, and this one is again still in Section B. It's question 7, and this one is all to do with bonding. So the first question is, thallium is in group 3 of the periodic table. Thallium reacts with halogens to form many compounds and ions. And it's asking us to draw the shape of the TLBr3, which is thallium tribromide ion, and the shape of the TLCl43- ion. Include any lone pairs of electrons that influence the shapes. Name the shape made by the atoms in TLBr3 and suggest a value for the bond angle. So they're asking us to do quite a few things in one question. Now, this is actually pretty tricky because we've got ions here. Now, if you're not sure on how to do bond angles or how to work them out, then I have done a few videos on bond angles. So just check on my bonding playlist and have a look for the videos on bond angles. So I'm just merely going to show you the method that I use to work them out for the purposes of this video. Okay, so the first thing we're going to do is we're going to work out the shape of TLBR3 first. So how I do it is I normally draw a dot cross diagram first, just to get an idea of how many bonding pairs and how many lone pairs I've got. So you can see here, we know that TL is in group 3. So I'm just going to draw our dot cross diagram here. And it has 3 electrons of its own. There's a 2- charge. Now this suggests that we have, for the purposes of working out the shape, that we add an extra 2 electrons to the TL in the middle. 3 of the electrons are actually being shared with bromine. So I'm going to draw them here. So there's the Br. And now it said we need 3 of these. Now the cross are the electrons originally belonging to TL, and the dots are the electrons involved in Br. Now I don't need to draw all the electrons for bromine here. It's just, like I say, it's just a part of the working method. And then we have the 2-. Now that means I've got to add 2 extra electrons to the TL. So what this tells us is it tells us how many bond pairs and lone pairs we've got. So I'm going to put bond pairs equals 3, and because we've got 3 bonding pairs there, and we've got a lone pair that has 1 lone pair on there. So if we add that up, that should give us a total of 4. Now what this tells us is it tells us what our shape is based on. So because this has 4 here, I can say that this is based, that our shape is based on a tetrahedral. Okay, so that's really important because it allows us to come up with our shape. Now, because it's based on a tetrahedral and we have a lone pair, then the shape is going to, or the angle, sorry, is going to change, but we'll come on to that in a minute. So I'm going to put TL. Now, normally with a tetrahedral, you'd have 1 going there, 1 bond, and you'll have 1, 2, 3, a little bit like a tripod. But the top bond here is actually going to be a lone pair of electrons because that's what we've got there. But all the rest of it remains the same. So we're going to draw bromine there, dotted line there. So that's in the plane of vision. That's going away from you if it's not a dotted line. And then the wedge tells us that it's coming towards us. Just going to shade that in. That's going to be BR. Right, now you can see this is, imagine this is a 3D. That's a bit like a tripod, and then you have the lone pair of electrons. So that's our shape, and that's got as the first mark. The shape of this is called pyramidal. It looks a little bit like a pyramid. And then when we get onto bond angle, which is this bit here, so the bond angle is actually what it would be if it was tetrahedral. Now, if it was tetrahedral, let's put it here, if it was tetrahedral, it'll be 109.5. But because we have a lone pair, for every lone pair that we have, we deduct 2.5 degrees from it. So with 1 lone pair, effectively the bond angle reduces by minus 2.5 degrees, and that reduces down to 107 degrees. So actually the bond angle here is 107 degrees, and that fits in there. Okay, so there's that first bit. It then also asks us to draw the shape of the TLCl43- ion, include any lone pairs of electrons that influence its shape. So we're going to start with, again, our dot cross. So we're going to start with TL. We have 4 electrons. We have 3 already in TL, but we've gained an extra 3. So in total, we've got 6 electrons with the TL. Now, 4 of them are involved in bonding. So I'm going to draw them just very quickly on here. Again, it doesn't really matter about the shape at this point. This is purely just working out. So dot cross, there you go. So there's our 4 chlorines. 1, 2, 3 electrons originally from the original atom of thallium. We've added an extra 3. 1 of them is involved in bonding, and that means we have 2 left over. So if we do our little sum over here, bond pair equals 4. Lone pair, as you can see, we've only got 1 of them, so that's 1. So this is 5. And what this means is that our shape is actually based on a trigonal bipyramidal shape. Okay, so when we draw this molecule, we need to have our TL in the middle, And trigonal bipyramidals means we have two polar groups which go top and bottom like that. Normally, you would have a bond coming out here and then two coming out here. We still have these two coming out here, so we'll draw the wedge. That's the one coming out towards us. And we'll draw the dotted line going away. But here you would normally have a bond here for trigonal bipyramidal. But because we've got one lone pair, we're just going to put our lone pair there. Now, it hasn't asked us to draw, name it, or it hasn't asked us to draw any bond angles on there either. So that's all we have to do. So this is a 4-mark question. So we're going to label where the marks are. You get 1 mark for drawing this bond angle, this shape. You get 1 mark for drawing this shape. You get 1 mark for mentioning that one's called pyramidal, and you also get 1 mark for saying that one is 107 degrees. So you get 4 marks in total there. Again, pretty tricky because we've got ions there, as you can see. All right, okay, so let's move on to the next question. And there we go. So we've got thallium-1 bromide, which is TLBr, is a crystalline solid with a melting point of 480 degrees Celsius. Suggest the type of bond present in thallium-1 bromide and state why the melting point is high. So what we're looking for is we're looking for the type of bond that exists between them. So as you can see, periodic table, thallium is down here in the periodic table, so it falls well into the metal area, and this is reacting with bromine, which is obviously a non-metal. So because we've got a metal and a non-metal, this tells us that it is ionic. So let's put that over there. So this is an ionic bond. Okay, and we need to say why it's got a high melting point. Now, in this point, when we're talking about the bonds were a lot stronger than intermolecular forces. So what we have here is with ionic bonds, we have a strong electrostatic attraction between, and this is between TL plus and Br minus. So in terms of the marks, we have 1 mark for actually saying ionic. We have 1 mark for saying that we have what we call a strong electrostatic attraction. So we get 1 mark there. And we get 1 mark for actually being specific by saying it's between TL plus and Br minus. So anything, generally ionic compounds have very high melting points because of this very strong attraction between oppositely charged ions which are there. So that, if you add them all up, you should get all 3 marks there. And then finally, the last question, we have to write an equation to show the formation of thallium bromide from its elements. So that's really important. Now, what I would do is I'd probably do this a little bit back to front, and I would have thallium bromide over there, and you can see the 2 elements that we need are thallium itself, and that's going to react with bromine. That's Br2. Bromine always goes around as a pair, so it must be Br2. You can't just leave it as Br. As you can see, that's not balanced, so what we have to do is we just put a half in front of the Br2, and that sorts it all out. So as you can see, that adds up. If you get all them, you should add up to 8 marks, and that actually completes this paper. That's it. Bye.